All right. Let's settle down and get started. First off, on the chair, you owe me a present. You owe me homework number 4, due today. I'm collecting them up here. Homework number 5 was posted today. It's on welded connections. It's due on the 15th. Again, it's a very quick assignment, and I think after today, if you had any trepidation at all about welds, that'll become not the case after this, after today. So yeah. One thing I'll mention, I went through and started updating and organizing the playlist for the class, the YouTube playlist, and it's up to date. There was an issue with the recording last time, and it got corrupted or it didn't record. I really don't know, but I had hit record just like I do every time. Oh, hold on, now I'm getting all freaked out. Let me make sure it's actually recording. But what happened last time is I thought it was recording. Okay, it's recording. And when I hit stop, it hadn't recorded anything, and it said that there was a corrupt file, and so we lost that recording. So what I did was this, in order to sort of make up for that. If you go to Blackboard, under lecture notes and handouts, there's another little thing on the bottom called example problems, and I posted the solution to the last 2 example problems that we did in class. Now, just so you're aware, in class this semester, they were examples 12 and 13. But the PDF I posted was from a few years ago, and in that semester, it was examples 11 and 12. But they're the exact same problems, and the solution is posted. So I figured that's the best way to rectify that was, since there's no recording, just post the solution to those problems on Blackboard. Everybody okay with that? Now, you tell me, is everybody good? I got the feeling I went a little fast last time. Did that sort of go over everybody's head? Did anybody have any questions? It's not dynamics. There was a stapler tossed. You missed it. Yeah, I know. Seriously, was everybody okay with last time? Did anybody have any questions? Everybody good? Okay. If you got any questions, again, please raise your hand. Don't be shy. I will be happy to address them. Okay. So last time we started to, let me go back a few slides. We started to, here's a good place. All right. So we started to dig into the spec a little bit in regards to how to determine the capacity of a fillet weld. And we had gone through all of the math associated with the weld metal, the base metal. We had gone through defining the ultimate capacity of a connection according to the weld metal capacity. So we said, all right, the phi value is 0.75. The material strength is 0.6 times the electrode capacity. And then the area is the length of the weld times the effective throat, so 0.707 times A from just sine and cosine 45 degrees. So the capacity was pretty straightforward. The base metal, you end up going off of section J4, specifically J4-2, because we're assuming everything is in shear. And so our capacity is just 0.6 times Fy AGV and 0.6 FU A and V. So it's very similar to the block shear computations. And remember, because we're talking about a welded connection and we're not talking about a bolted connection, because we're not drilling holes or anything, the net area in shear equals the gross area in shear. We have our phi values listed, pretty straightforward. We do have minimum and maximum weld sizes for similar but different reasons than for bolted connections. For welded connections, we're worried about 2 things. We're worried about the heat sink phenomenon. So we have a minimum size of welds listed because if the weld gets too small, if you have a super thick plate and a really tiny weld, you have that heat sink phenomenon, and you get sort of an issue or a situation where the plate absorbs the heat really rapidly, and you get a rapidly cooled weld. It gets pretty brittle, and it doesn't behave properly. So we have a minimum weld size limit for that heat sink phenomenon. The maximum weld size limit is essentially to maintain this. If you have a what I would call a regular plate. The maximum weld size is usually backed off 1/16 of an inch because we want to try and avoid melting that corner tip of the plate as we're placing the weld. Now, if we have a really thin plate, something that's like less than 1/4 inches thick, we say, don't worry about it. Go ahead and melt it. It's not really going to matter anyways. So, so that's sort of our reasoning for weld limits. Minimums are to prevent the heat sink phenomenon, and maximums are to maintain the geometry of the plate. Make sure that it remains a rectangular plate. I did mention weld limits on length, but that's usually not an issue for most of the welds that we're placing. And so we got this, a very concise summary of equations. This is the weld metal capacity, base metal shear yielding, base metal shear fracture. We have our minimum weld sizes that we look up, and our maximum weld size is either the thickness or the thickness minus the 16th. And most times it's going to be the thickness minus the 16th. We did 2 examples. One was an analysis example and one was a design example. In the design process, it's pretty straightforward. You just assume the capacity of an inch, or determine the capacity of an inch of weld and divide it by the load to determine the total number of inches. That's really basically it. The only thing, I guess, on top of that is that usually when you're in design mode, you have to determine your weld size, and more often than not, you want to choose the maximum weld size. Maximum weld size means shortest weld length, and so that's typically going to be the most economical. And when choosing a weld size, usually what you're wanting to do is choose the biggest weld size that you can, but you don't want to go over 5/16. And the reason why is 5/16 is about the largest weld size that you can place with a single pass of your electrode. Now, if you've got a lot of load and you just need a bigger weld, well then, I mean, you just need a bigger weld. But usually we can get by with using only 5/16 or less, depending upon your weld limits. And so 5/16 is a very, very common weld size because of that. Any questions? Okay. Now, this was the example that we did last time. And so when we did the math, we ended up solving for a weld size that was something along the lines of, I think it was like a weld length of something like 11.8 inches. Was it something like that? Is that what we got? I don't remember. What was the number? Was it 11.78. So we rounded it up to 12 inches, and what we did is we said, well, this is a plate, so let's just put 6 inches up here, 6 inches down here, let's just call it a day, right? Well, I think that made sense. If you've got 12 inches, just do half and half. But why? Like, why would we split it up half and half? Like, why don't we just put 12 inches up top and nothing down below? Is there any reason not to? Well, yeah, there is a reason not to. The reason that you don't is sort of think of it like a beam. I'm yanking on this plate with, what was the force on this problem? It was like 80 something. Because there was like a dead load and a live load. We factored it. What did we get? 82 kips. So I'm placing 82,000 pounds on this plate. And so the analogy that I think of is this. Imagine that I'm sitting on, or I've got 82,000 kips sitting on the middle of this table. Half of it goes here and half of it goes here, right? So wouldn't it make sense that if I'm placing weld, I would place half my weld over here and half my weld over here, right? So what if I didn't? What would happen if I placed half or all of the weld on one side and none of the weld on the other? What would happen from a capacity standpoint? Well, what would happen is you'd have an eccentricity. You'd end up basically generating a moment in the connection because you have got all your weld on one side and none on the other. And if you're yanking it through the middle, you're going to want to cause that plate to bend a little bit. And that bending is something that we're not intending. I mean, here's the member, and I'm intending to just yank on it with 82,000 pounds. Well, if I place the load, if I place all the weld on one side and none on the other, not only am I going to have that 82,000 pounds, but I'm going to have an eccentricity. Okay? And so I want to sort of avoid that. Now, what we did unintentionally with this problem is we placed what's called a balanced weld. Okay? And that, what I mean by balanced weld is a weld configuration that is intended to eliminate moments. Okay? Now, it's pretty easy to do that when the plate is symmetric. Just put half on top and half on the bottom, and you're good. Okay? But what about if the member is not symmetric? What if you have a member that's something like, I don't know, an angle? Okay? An angle does not exhibit symmetry up and down, because if you have an angle that's, you know, like an L 8 by 8 by 1, the centroid is not 4 inches down. It's whatever X bar and Y bar is. So because of that, the configuration and the way that you place welds is not as simple as just half and half. We have to place those welds in a certain fashion in order to eliminate bending moments. And so what I want to show you today is how to place a balanced weld arrangement. Okay? And I think you're going to find this is pretty straightforward when you get into it. And we're going to look at the following example. Okay? So I have a connection. And so a lot of this is going to feel like a repeat of what we did in the last example. But what we do at the end is going to be pretty new. I have an angle affixed to a gusset plate. And we'll say that it's A 572 grade 50 steel throughout. And when I have this note here, I say assume the capacity of the gusset plate to be adequate. That just means for the sake of this problem, I'm just really ignoring the gusset plate, and all I'm doing is I'm looking at the angle. Okay? So what I have here is I have an angle. It's a 6 by 4 by 3/8 inch angle, and I'm going to design balanced fillet welds to resist this, this angle. Okay? So let's sort of go through this step by step. And I think you'll see how this is a pretty straightforward problem once you get into it. And once we do this problem, I think you'll see how we arranged the welds in our previous problem not only just seemed to make sense, but it would follow along this pattern as well. And so let's just sort of dive right into it. Okay, so first off, we're designing this connection to withstand a factored load of PU is 150 kips. Do I need to factor that or anything? No, it's already been factored. If I had given you like a service dead load and a service live load, then you need to factor it. Okay. Now let's look at material properties. First off, we were given E70 electrodes. So that means that FEXX is 70 KSI. So just the number. All right? And we were also given A572 grade 50 steel. So we have FY and FU are what? What's that? It's going to be 50 KSI. This is 65 KSI. Okay, is everybody okay with that? I don't want to go too fast. So. All right. Now, in order to design a welded connection, basically what we're trying to do is determine the capacity of an inch of weld. But in order to determine the capacity of an inch of weld, we need to know how big the actual weld size is. Remember, a weld is sort of like a triangular cross-section, and so we need to know the size of that weld. So what we're going to do is we're going to go to our weld limits. In order to try and determine a minimum weld size and a maximum weld size. Now, let's start off with A min. What is A min going to be for this section? Now, first off, can you calculate A min? No. A min is a lookup. Okay, you're saying 3/16 of an inch. Okay, so first off, where did you get that? So everybody should have their AISC 15th edition steel construction manual with them. at all times when they're in CE 414 structural steel design here at Marshall University, right? And so we're in table J2.4. Okay. All right. Pretty good. Most people have it with them. I like it. Now, I still see a couple that don't. Now, what did you say again? What was the weld size? Okay, you said 3/16 of an inch. Now, first off, do I have a second on that value? Yeah. Okay, now why did you say that, though? Because the thickness is 3/8. We're talking about that angle that has a thickness of 3/8. Okay? All right, so that's why we utilize this value. Now, as for A max, now this one is one that we can compute. Okay? A max we can compute. So remember, the minimum weld size is off that heat sink phenomenon. The maximum weld size is off of either the thickness or the thickness minus a 16th. So which one are we going off of? Thickness minus a 16th. The plate is, or the angle, which is essentially just a plate being all bent up. The plate is definitely thicker than 1/4 of an inch. So that is the thickness minus a 16th of an inch. So that is 3/8 minus a 16th. So 3/8 is 6/16. 6/16 minus 1 is 5/16 of an inch. So, excuse me. So you have an A min and an A max. Typically, when you're selecting weld sizes, do you lean towards the minimum weld size or do you lean towards the maximum weld size? Maximum. A larger weld size means a shorter weld length, and generally a shorter weld length is more economical. And so when you're choosing weld sizes, you want to get as close to 5/16 without going over. Can we choose 5/16? Yeah, okay, so therefore, use A is 5/16. Okay, everybody good? Now we're going to take this one step at a time. Capacity of 1 inch of weld. Okay? So what parameters do we know? Okay? We know that FEXX is 70 KSI. We know that A is 5/16. We know that the length of weld is going to be 1 inch. Like we're assuming right now for the sake of discussion that the length of the weld is 1 inch. Okay? Bless you. We know that Fy is 50 KSI. We know that Fu is 65 KSI. And we know that the thickness is 3/8. So before we start computing capacities, is there anything that we can compute right now? If we know the length of the weld, because we're saying it's 1 inch, and we know the thickness, what can we compute? There we go. We can compute the gross area in shear, and we can also compute the net area in shear. So we can say that AGV, now remember that equals ANV because we're talking about a weld. We're not drilling through the plate, so we don't have to remove material to create a connection. And so that's just LW times the thickness. So 1 inch, 3/8. 0.375 square inches. Sound good? All right, so for the weld metal, we have phi RN is phi times 0.60 FEXX times 0.707 ALW. And do I need to fill all this in? I mean, we have all the values. Remind me, what's phi for the weld metal capacity? It is 0.75. So can I just have you all tell me what this is? You tell me. We have 0.75, 0.6. This is what, 70? This is 5/16, and that's 1. So tell me what you get. 6.96. Do I have a second on that? If you need me to wait a little bit, that's fine. I mean, everybody good? Okay, all right. So this is 6.96 kips per inch. And I say kips per inch, even though the units don't really work out that way, but I'm saying kips per inch to indicate that that is the capacity per inch of weld. So now we have the base metal shear yielding. Now, what was the phi value for this? 1. Okay. And so this is phi RN, and that's phi 0.6 FY AGV, and that equals what? Say it again. 11.25. Do I have a second on that? And base metal shear fracture. And phi for this one was what? Yep. And so this is phi RN. This is 0.6 FU A and V. Do these numbers seem familiar, by the way? They're exactly the same ones. And so I went through example 13 pretty fast. I'm going through this one a little bit more measured, make sure everybody's following along. And so what does this one come out to be? I heard somebody, what somebody? 10.97. And so in design mode, which one is going to govern? The smallest one, right? Because what I'm going to be doing, if I'm designing this weld, you know, if I use this might say I only need 10 inches of weld. This might say I need 15 or 16 inches of weld. So I always use the one that's the worst case scenario. So this is the one that governs. And so phi RN, sorry. So I want everybody to be clear. Phi RN for this connection is 6.96 kips per inch. Now, hopefully, up until now, this was a little boring. Is this hard? I mean, I would hope. I mean, if you have a question, please. I mean, I'm not. You know, I mean, that's what we're here for. Everybody good? Now, here's the new stuff. Here's the new stuff. Balanced arrangement. Okay. Whoa. Got a little bit of wet ahead of me. Okay. Now, in order to lay out this balanced arrangement, I'm going to put two numbers up top. I'm going to say PU is 150 kips. And I'm going to put phi RN is 6.96 kips per inch. You don't have to rewrite them if you don't want to. I'm just putting them on my screen so that they're there. Okay. Let's draw some things out. Now, I have an angle that looks something like this. Okay? And I have a line that goes something like this. Okay, here, let me move that over a bit. Okay. Now, I'm looking at this angle on the side. If I look at it, what are we, samurai sword or lightsaber if you're a sci-fi fan, what does the angle really look like? It looks, in a cross-section perspective, looks like this. Okay? In fact, let me redraw that a little bit. Say it's like that. Okay. So what I mean by that, bless you, is this is 4 inches. And this is 6 inches. Okay? So this dimension here so that everybody's clear, that is 6 inches. Now, I have a question for you. How far is it from the bottom of this angle to the centroid? Bless you. I want to know what this dimension is right there. How far is it from the bottom to the centroid? Now remember, just so everybody's clear. Actually, let me do that another call. This is an L6 by 4 by 3/8. How far is it from the bottom to the centroid? So this is going to involve you going to the section properties table, looking at the actual image up top. I heard a number of 1.93. Is anybody seconding that? That is exactly right. And so what is that? Is that an X bar, Y bar? What is that? Y bar. Now, is everybody able to find that? Okay, so I'll put that up here. So we'll say Y bar is 1.93 inches, and that's from table 1.7 on page 1-what? Is everybody able to find that? If not, let me know. It's okay. Remember, we don't look up the XP or the YP. It's always the Y bar. And the reason that we're looking up the Y bar is we're assuming this angle is welded on its long leg. If it was welded on its short leg, we'd be using the X bar, right? That's a good question. Sorry, excuse me. That's a good question. And honestly, it should have been on the problem, and it's not on the problem. But let me say this. In actuality, in most instances, if you have an angle that's longer on one leg than it is on another, usually you're connecting to that long leg anyways. So, everybody with me? Okay. Now, here's the reason that we need the centroid. What we're doing in this problem is that we're assuming that the load on this connection is going through the centroid. that when we yank on this angle with a load of 150 kips, we assume it goes through the centroid. Remember, when you use sigma equals P over A from the wonderful Engineering 216 Mechanics of Deformable Bodies, you are assuming that those loads go through the centroid. If the load does not go through the centroid, not only are you generating axial load, but you're bending the section as well. It's like if I have this backpack on my back and it's off to the side. Not only do I have to hold the backpack up, but I have to sort of keep my back from tilting if the backpack's all the way over here. So the only way I can ensure that I'm not being jerked over this way is if the backpack is going right along my center axis. Make sense? Now the problem is this is 1.93 inches. So does everybody see how the load is closer to this side of the angle than it is to this side of the angle? Everybody see that? So as a result, I propose that when we place weld, we're going to have more weld on this side than we are up here. That's what I mean by a balanced connection, that we're going to have more weld on the bottom than we are on the top because the centroid is closer to the bottom than it is to the top. Now what I'm going to do for this problem is I'm actually going to assume that there are 3 welds on this connection. I'm going to assume that I have a weld on the bottom, a weld on the top, and I'm going to go ahead and place a transverse weld on this as well. I'm going to go ahead and put a weld right here. Okay? Now, the load is yanking on the angle that way. So the welds are resisting the load that way. So I propose that there are 3 forces being developed by these welds. A force here, a force here, and a force here. So we'll call them F1, F2, F3. Now, let's look at weld number 2. How long is weld number 2? 6 inches long. I don't need to do any design to figure out how long weld number 2 is. It's 6 inches long. Another thing to keep in mind, this is just a single line of weld. So does anybody wager a guess as to what that distance is? Like where does that force, where's the resultant of that force? 3 inches, halfway up, right? So this is 3 inches. Okay, so I propose, before we do anything, that F2 is going to be 6.96 kips per inch times a distance of 6 inches, which equals what? Close to like 40 something. 41.76 kips. Do I have a second on that? So think, the welds can withstand a force of 6.96 kips per inch. That weld is 6 inches long. So that's how much that weld can withstand. And so what I want to do is I want to try and figure out how much force the remaining 2 welds need to withstand. And how am I going to do that? I'm going to break out sum of moments equals 0. Specifically, sum of moments about the bottom. So you all know the drill. So what we're doing is we're summing moments about the bottom of the angle. Okay? So we have 4 forces we need to consider. Let's start off with the forces going that way. Are there any forces going that way? PU, right? So about the bottom of the angle, are we rotating this way or this way? Do we belong on the left side or the right side? Left side. And from the bottom of the angle, how far are we? 1.93 inches. Or symbolically, we could say PU times Y bar. Now, how many forces are going this way? 1, 2, 3 of them, right? Let's take each one at a time. What about F1? Which side does it go on, the left or the right? And what's that moment arm? There we go. What about F2? Is it on the right? And what's that moment arm? What about F3? What's its moment arm going to be? There we go. So we have PU times Y bar equals F1 times 6 inches plus F2 times 3 inches, right? Let me squinch this up a bit. All right. So therefore, what don't I know in this expression? What don't I know? F1. So what do? I say, all right, let's put that F2 times 3 inches on the other end, divide by 6. F1 is PU times Y bar minus F2 times 3 inches over 6 inches. So and so what does that come out to be? Say it again. 27.37 kips. Do I have a second on that? Now, let me ask you this. How long does that weld need to be? How do I determine that? There you go. So therefore, we'll call that L1 is 27.37 kips over 6.96 kips per inch. And that equals what? Say it again. So just use a 4-inch weld. Now, if you're paying attention, how do I determine L3? Or how do I determine F3? Let's keep it simple. There you go, sum of forces in the x direction. So if I just say, all right, let's sum forces in the x direction, I can just say that F3 is the force going to the right minus the remaining forces going to the left. And what do I get? Say it again. Then do the same thing. And that equals what? Sorry, that's L3, not L2. Now, I was drawing the box. As I drew the box, I saw the mistake. Does that count? I'm going to say no. I know, it's skewed because I'm the one who keeps track of it. All right, so to summarize this welded connection design, here's the angle. And so what you've got is you've got, and you don't actually have to draw the weld symbols or like the actual weld, although I like to draw that out. We have that. We have that. We have that. And so this is 5/16, 4. 5/16, 12. 5/16, 6. That's a balanced connection, okay? Now, if you go back to our previous example, the math would have gotten a whole lot easier, a whole lot faster, because, and the reason is because of the location of the centroid. The centroid is not some 1.93 inches, some weird dimension. It was just a plate. The centroid was halfway up. So think about it in terms of beam reactions. If I have a load right in the middle, the reactions are half and half. That's it. So that'd have been all there is to it. Did this make sense? Anybody have any questions? What? It's the opposite. Never use only a transverse weld. I thought that's what you said. It's a, well, I mean, we did. That's right here. Are you,
I know. I'm saying
how do you know when to do it and when to don't? Okay. There's nothing wrong with placing a transverse weld as long as you have a longitudinal weld to go with it. That's the short answer. I have no problem with placing transverse welds. In fact, on a connection like this, I would almost advocate it because it would make the connection shorter. Okay? Imagine if we didn't place a transverse weld. This weld is gone, so that means these two welds are going to get a little longer, which means the connection plate that it's connected to has got to get a little longer. And so imagine repeating that throughout the system.
that's what I'm saying. So it doesn't, like, there's no effect on the moment whether the welds in the transverse section.
No effect on the moment.
Like, because you're factoring the transverse weld into your calculation.
Yes.
If you don't use the transverse weld, there's no difference in your calculation.
Well, that's a great question. So the only thing that would be a difference is this. What would F2 be? It'd be 0 because you just wouldn't have one. So everything would be the same except you just wouldn't have an F2. So it's not like saying, oh, well, this is 3 inches longer and this is 3 inches longer, so we'll just split. It gets washed out through the statics. Because your homework problem, I believe you don't have I'm making you do it without a transverse weld. Daddy, if you can do this is harder because you have to account for it. I don't know if harder is the right answer because I don't really think this is that hard. I mean, is there any questions? Yes. Yes. Because typically, if you're going to place that, you're just going to weld around the whole thing. Yeah. So, yes. Any other questions? Well, I have two things to say before we at least introduce our next topic. Number one, if you understood that, then your homework assignment should be a breeze. I'm not kidding. Two, that's exam 2. Because exam 2 is just on bolts and welds. That's it. There's a reason why exam 2 is only worth 15%, because it's just not on a lot. All right. We're introducing this next topic, though. Let me go say this. All right, so let's everybody pay attention. Are there any more questions on welds? Seriously. Then that's all I have to say about them because there really isn't much else to say. It's pretty straightforward. There are some more advanced connection types that you can design, like if you have eccentrically loaded connections and things like that. But for regular old everyday purposes in a typical steel design course, that's it. And so we're going to move on and cover the first of our last two remaining topics, which are columns and beams. And I'll go ahead and tell you that things from here on out are going to get a little different in terms of how we design, the theories that we consider, the math that we look at. It's going to get a little different. Okay? What we do from here on out is going to be much more heavily dependent on design aids in the manual. It's not going to be like what we did just now where we could just solve for the weld length and then move on. Yes? That's a good question, calculus. There'll be some calculus that shows up in the derivations, but not in the actual problems. So, what's that? Oh, God. All right. I want to talk about a concept that was discussed at the end of Engineering 216. I know it's still burned into your memory, but I'll recap. And that's the concept of buckling. How many of you have heard of buckling? Hopefully. Okay, good. All right, so the idea behind buckling is this, is that when you take a member and you yank on it, it will, you can yank on it all day long until you hit the yield stress or the tensile stress or what have you, and there you go. But when you load something in compression, it's a little different. Imagine if I had a yardstick in my hands. I can yank on that yardstick all day long, but as soon as I take that yardstick and I start pressing on it, it starts suddenly bowing, and it starts bowing very rapidly. Like you load and load and load, and then boom, it goes. Now, how do you address that? Well, you address that through basically a whole different science in structural engineering, and it's a major topic that we have to assess, and it's the idea of stability. And I would argue that stability and the concept of stability is really going to become a main focus of this course for the rest of the semester, because whether we're looking at columns or we're looking at beams, stability becomes a big deal. Okay? Now, we have, what we're going to do is this, and I'm going to sort of save this and really get into this next time, but we have a column, we have a pin column, we have a load on it, and we're going to apply a load P, and we're going to say, well, how much load would cause that column to buckle? What we're going to do is this. We're going to go through all of the math associated with buckling, okay? I know if you've had me for mechanics of deformable bodies, we derive this at the end. If you haven't, I know you've seen it at some point, but at the very least, even if it's been a long time, you should remember a formula that looks something like this. I know it's been a while, but you should have seen it at some point. What we're going to do is this. I'm going to derive this formula for you. We'll walk through it together. And then what I'm going to do is I'm going to tell you why that formula is wrong. Okay? Now, you're going, Dr. Mike, what are you talking about? Why are you wasting our time? Here's the reason. Here's the reason. Elastic buckling is not in itself entirely correct, but it's useful. Okay? What we're going to do is ultimately use this formulation when we compute capacity, but there's two big reasons why elastic buckling and why what you learned in 216 doesn't directly work for columns. We're going to talk about that next time. Before we end, so I see everybody's like, yeah, Dr. Mike, but we're packing up because we got lunch to eat and all that. I still got about 7 or 8 homework assignments on the cart. Go get them. This guy right here. Hi. How's it going, man? Get your homework assignments. That's all I got.